Hi, this is your instructor, Jerry Pinter again. Welcome to Chapter 2 on LTI systems. In this first part of our video lecture, we will be looking at impulse response and convolution for discrete time systems. So Chapter 2 is broken up into 5 parts because it's a rather lengthy chapter. So this is just a description of each of the 5 parts that we will be doing in separate videos. In this video, we're going to be dealing with part 1. I should also mention that in addition to these 5 videos, there is some additional material that can be found in the lecture notes, which will be posted on Cougar Courses. There is an appendix on solving linear differential equations and also some optional material on finding a system's impulse response that we will not be covering in this course. So let's get started with part 1 of this chapter. So we'll start with a quick review of linear time invariant systems, or LTI systems, because that's really the focus and the main point of this chapter. So we introduced the idea of an LTI system back in the end of chapter 1. So a linear time invariant system has 2 properties. It's linear and it's time invariant. So linearity just means that if we scale the input, then the output gets scaled by the same number. So to see an example of what I mean here, look at this diagram here. This is our standard configuration for a system. We have an input sequence x of n going in, and the system processes that input and spits out an output called y sub n. Now, if we were to multiply this input, whatever it is, if we were to multiply it by, say, a factor of 5 in front, then the output also gets increased by that same factor of 5. So this is what we mean by linearity. And there's a little more to linearity. For example, if there are several inputs present at the same time, remember that we just have to add up all of the individual outputs for each input. This is the principle of superposition. And again, this is something we introduced back in chapter 1. Now, what about time invariance? Well, this just means that the output is delayed by the same as the input. So going back to this picture here, this input sequence here, x of n, if we were to delay it by 2 counts, so it's x of n minus 2, then the output is also delayed or shifted by the same amount, those 2 counts. So one of the key concepts of this chapter is the idea of the impulse response of a system. So remember that the simplest input signal to a system is a single unit impulse, and that's shown right here. In discrete time, which is what we're dealing with in this part of the video, an impulse is just a single value of 1 that sits when n is equal to 0. And this impulse or delta function is designated by the delta symbol here. So this is delta of n, which is an impulse. So if we feed this into a system, then the system is obviously going to respond to this impulse. So the output of the system is called the impulse response. Makes sense. And the impulse response, it's conventional to use the letter H for impulse response. So delta of n goes into the system, H of n comes out. Now, what does this impulse response look like? Well, this is just an example or a hypothetical example of what an impulse response might look like. Obviously, it's going to depend on what's inside of this system. Okay, so the importance here, though, is that the unit impulse response, h of n, because we can use superposition, we can construct the output y of n for any input x of n just by scaling and shifting h of n. And this is something that we're going to explain in more detail in the next several slides. The main idea right now is that the unit impulse response completely characterizes the system. In other words, by just putting in this simple signal, this impulse, into a system and seeing how it responds and what it spits out, we can learn everything we would ever want to know about this system. So, this is in other words, this impulse response, h of n, is a very important property of a system, because it pretty much tells us everything we're going to need to know. And that's one of the things we'll be expanding on, not only in this chapter, but in the multiple chapters that follow, is we'll be learning how to analyze this impulse response, both in the time domain and later on in the frequency domain, in order to learn about this system and what's inside this box here. So we can do a little bit more with this impulse. In fact, we can learn more when we scale or shift the impulse and look at the scaled and shifted impulse response. So to see what I mean here, remember, this is what we just showed in the last slide. Here we have a unit impulse, delta of n, and that goes into the system, and then the output of the system is h of n, which is the impulse response. Let's just say it looks like this for this particular system here. So what happens if we take our impulse here and we shift it over by k values? So in other words, we're shifting it over or delaying it k values. So our input now is delta of n minus k, which is just a shift. And our output, because remember this is a time invariant system, our output will also be shifted by k. So notice this output here looks exactly like this one up here. The only difference is instead of starting at 0, it's shifted over and it starts at k. So this is due to time invariance. Now, suppose we have some sequence x of n, all right, that looks something like this. And the kth value of x of n is this shown in red here. It's x of k, which is a number. So if we multiply this shifted impulse here by the value of x of k, then we get this. We get our input is mathematically written as x of k times delta of n minus k. Graphically, it looks like this. When n is equal to k, right here, we get an impulse, but the impulse doesn't have the value of 1. The impulse has the value of x of k, because we're simply multiplying x of k times this impulse. So what does that do to the output right here? Well, what happens is this output now gets scaled by the value of x of k. This is linearity. Remember, if we multiply our input by some number, the output gets multiplied by the same number. So you can see here, this output here looks like this one, except everything is taller because everything has been scaled by the value of x of k. So for example, if x of k has a value of 3, then all of these values that are shown here are going to be multiplied by 3. So this is, this output here is the result of two properties of this system. It's linear and it's time invariant. So let's go ahead and do an activity or example to help test and see your comprehension of applying these ideas of linearity and time invariance. So let's suppose that you're given the following impulse response, h of n, right here. So it's a pretty simple impulse response. Notice when n is equal to 0, it spits out a 2, and then when n is 1, we get a 1. So this is the output for an impulse, a delta of n function. Now the question is, what is the output of this same system if we put this into it? So notice there's a 2, a 3, and a 4, all one after the other. What will we get for our output here? And to figure this out, all you have to know is this, the impulse response here, and these values here and where they are. So the hint here is treat each of these values here, these inputs, individually as scaled and shifted impulses, and determine the output for each member of x of n separately as scaled and shifted versions of h of n, and then finally use superposition to add all the results together to get y of n. So go ahead and pause the video and see if you can figure out what the output here, y of n, of this system would be given this and this. All right, so here's the solution. And to do this, it's actually pretty simple once you get the hang of it. So here, remember our input was a 2, a 3, and a 4, and our impulse response was a 2 and a 1. So let's take this signal here, this x of n, and break it up into 3 separate signals. Here's the first one, which is the 2. Here's the 3 here, and here's the 4 here. And notice they are, of course, shifted to where they are up here when n is 0, 1, and 2. So what the problem comes down to is we need to figure out what does the system do when it sees this by itself. Well, we know if this were a 1, it would just produce a 2 and a 1, because that's the impulse response by definition. But it's not a 1, it's a 2. But all that 2 does is scale it. So instead of getting a 2 and a 1, we get a 4 and a 2. All right, so this is the output just due to this part of the input. Now the next part of the input is this 3 right here, which is, the center value up here of x of n. This is x of 1. So what does this 3 do? Well, the 3 just takes this and multiplies everything by 3. So we get, instead of a 2 and a 1, we get a 6 and a 3. But also remember, this 3 is shifted over 1. It's sitting at n equal 1, not n equals 0. So the 6 and the 3 have to start at 1 and then go to n equal 2 instead of starting here at 0. The last one, there's a 4 up here, so that's what's shown here. Well, this 4 scales the impulse response by a factor of 4. So instead of 2, 1, we get 8, 4, but remember, where is this 4 that's coming in? It's sitting at n equal 2. So the output for this particular 4 here is going to start when n is equal to 2. So here's the 8 and the 4, and notice it's shifted over accordingly. So these are the 3 separate outputs for each part of the input, and by linearity and superposition, all we have to do are add these 3 outputs together to get our total output. So you can see when n is equal to 0, we have a 4, a 0, and a 0, which gives us a 4. When n is 1, we have a 2, a 6, and a 0. That gives us an 8 right here. When n is equal to 2, we have a 0, a 3, and an 8. 3 and 8 gives us 11. And then finally, when n is equal to 3, we have a 0, and a 4, which is the 4. So here's our final output. This is the answer to the problem. Our output is 4, 8, 11, and 4. Okay, so make sure you understand how I did this. Once you see the method, it's actually pretty simple and basic. You can just do the math in your head, and you just have to keep track of, making sure you scale everything appropriately and shift everything appropriately, and then add up all the results to get our answer. By the way, what we just did is something that's called convolution, or a convolution sum. And this is probably the main topic, the most important topic of this chapter is the idea of convolution. So the result here, y of n, is written actually as x of n. This star here doesn't mean multiply. This is the convolution operator. So it's x of n convolution with h of n. So this is the input, x of n, up here, convoluted or convolution with the impulse response h of n, which was given up here, and that gives us the output. Now, how do you figure out the convolution of 2 sequences like this? Just like we did here. So that last activity was actually, our first example of a convolution in discrete time, and we're going to look at this a little bit more in this part of our lecture coming up now. So let's just quickly again review the discrete time sampling or sifting property. It said that x of k, in other words, the kth value of a sequence x of n, is given by the sum from n over all n of x of n times a delta function of k minus n. And one of the things that you can do with expressions like this is swap the roles of the indices, and sometimes this is called index gymnastics. And so basically wherever we see a k up here, we replace it with an n, and wherever we see an n, we replace it with a k, and we get this expression right here, which is also true. Now this expression here has 2 interpretations. we can think of the sampling property in that this delta function is sampling now the nth value of the sequence x of k to give us x of n. But in this section of the lecture, this second interpretation is actually a little more relevant. The one way to think of this is that the sequence x of n here, it's represented as a weighted sum of shifted unit impulses. Now, what do I mean by that? Well, basically what this is saying inside the red box here is that let's say we have some sequence x of n that looks like this. X of n we can think of as broken apart as all of its individual values and added together. So, this first value here is shown right here. The second value here is the second term. The tall one right here is the third term, which is shown here, and then finally the fourth one over here. Now, each of these individual terms here that are added together can be represented by x of 0 times a delta function, x of 1 times a delta function that's shifted over by 1, x of 2 multiplied by a delta function that's shifted over by 2, and so forth. So when we add all these together, when we add all these terms together, we get exactly this summation shown here on the right side of this equation. So let's take this a little further now. This slide here, we already went through this slide, but I'm just going to review it because this sets us up for the meaning of convolution. So remember, if we have a unit impulse, delta of n, then the system outputs its impulse response, h of n, which let's say looks something like this. If we shift that unit impulse over by k, here it is over here now at k, then our output just gets shifted over and it starts at k instead of starting at 0. All right, this is time invariance. So delta of n minus k here gives us h of n minus k at the output. Now, suppose we have some sequence x of n, and the kth value of x of n is shown in red here. It's x of k, which is just some number. If we multiply this number by this shifted delta function here, then we have x of k times delta of n minus k, and it looks like this. So this looks just like this here, except instead of having a height of 1, it has a height of x of k because it's been scaled by that value x of k. What does that do to the output over here? Well, the output also gets scaled by x of k. So the output is x of k times h of n minus k, and it looks just like this, except it's perhaps taller now depending on the value of x of k. All right, so this, we actually did this slide earlier, but what we're going to do now is take this another step. So let's take the result from the last slide where we showed that x of k times delta of n minus k gives us x of k times h of n minus k, and let's use superposition and sum this over all k. All right, now we're allowed to do this because this is a linear system. When we sum up all of these terms over here, shown here with the sigma or summation symbol, then by superposition, the output gets summed up as well because this is a linear system. So the output now is just the sum of all of these outputs here for all the different values of k. Now, why did we do this? Obviously, this is getting a little confusing here, but why would we want to do all this? Well, look at this on the left side. If you look a couple slides ago, this summation on the left side is shown right here, and it's exactly equal to x of n, the original sequence. So what this means is that if we take any sequence, x of n, this is our input sequence, all right? It can be anything. We know the output is given by this over here, because remember, all of this junk here on the left is just x of n, which is shown here. This is what we're looking for. This is the output of the system. This is our output sequence y of n, and it's given by the sum over all k of x of k times h of n minus k. So this, again, I know this is not super clear yet, but this is a formula for how to calculate the output of any system if we know the input x of n, That has to be given, obviously. And we also have to know what the impulse response is, because remember, the impulse response is h of n. But if we know those two things, we can do this summation here and figure out what the output of the system is. So what we just did was derive what is called the convolution sum. So the results on the previous page are extremely important and useful. It gives the system's output sequence y of n for any input sequence x of n, just by knowing the impulse response h of n. So again, this kind of reminds us why the impulse response is so important. If we know what the impulse response is to a system, we can figure out its output to any signal, all right, given by this, the convolution sum, which is just a repeat of what was shown on the last slide. Instead of writing out this whole thing, which is, kind of complicated because it's got all the indexes here and the h and the n and all that, the convolution sum is designated with this star symbol here. So in signals and systems, the asterisk or the star, it doesn't mean multiplication, it means convolution. So y is equal to the convolution of x and n, and the convolution of x and n is given by this sum right here. Okay, so again, this tells us that whatever the input of the system is, the output is always equal to the convolution of the input with the impulse response h. So for discrete time systems, there are actually two ways to compute the convolution sum. The way that we just learned a few slides back in the activity, I think is much easier and sort of more intuitive than the way the book describes how to do it. So I'm going to show you both methods here, and my advice would be for discrete time, I would use this method that I think is much easier. And this is actually not shown in your book. So again, we did this example, so I'm not going to go into it in great detail again, but let's say you're given an input sequence x of n, and you're given the impulse response h of n, which is shown here. So your goal obviously is to find the output of the system for this input here. So the way you do it, remember, from a few slides back, you take x of n and you break it up into its individual pieces. And you find the output to each piece by simply scaling the impulse response by whatever the value is here. So this value of 2 made the 2, 1 become a 4, 2. The 3 made 2, 1 become 6, 3, and the 4 made it become 8, 4. But then also remember, you have to shift them accordingly. The first one here is at 0, so that's going to stay starting at 0. But the 3 here is shifted over, because, it's at when n is equal to 1. So remember we had to shift the output over 1. And then the 4, we had to shift it over 2. But then all you have to do is add these together. You add them for each value of n, and we already did this. We ended up with 4, 8, 11, and 4, and this is the convolution of x and n. So this is the output. So I believe that this is much simpler to do than the book method, which just for completeness, I am going to go over it, but I'm going to go over it kind of briefly, and I'll let you, as a student, decide which method you might want to use, for example, in the homework when you have to do these types of problems. So here's the textbook formal method of computing the convolution sum. And basically what the textbook does is, and this is the formal definition of a convolution sum. Y of n is equal to the sum over all k of x of k times h of n minus k. All right, so how do we do this? Well, you've got x of n here, and you've got h of n here. Those are given to us. So notice our output here, there's no x of n, there's an x of k. So let's rename x of n to x of k. Well, that's easy enough. We just take this and we just call it x of k instead of x of n. Obviously, this index here, our time index, becomes k now. Now, what about h of n? Well, notice h of n has to go to h of n minus k. So the first thing we're going to do is we're going to find h of minus k. So we change the n to minus k. Now, so the first thing, we can change n to k, and we get this here. And h of minus k is a time reversal, which means we have to flip h of k about, k equals 0. So it's sort of the mirror image. All right, so that looks like this. And then h of n minus k, remember this is a shifted version of h of minus k. So let's start with n being some value less than 0. Then that's going to move this sequence here over by n to the left. So notice, here's k equals 0 over here. So we've got this thing way out here. All right, so let's keep going. So now what we need to do, if we look at, the output formula here, we need to multiply x of k, which is shown here, times h of n minus k, which is shown over here. Remember, it's been shifted. We need to multiply them together. Well, you can see there's no overlap between the two sequences. So there's going to be no product here. The product is always going to be 0. This just tells us that the output is 0 for n is less than 0. But now we have to slide h of n minus k over to the right, all right, by increasing the value of n. N was negative in this case here. And when we do that, we do it until we finally see an overlap here. So when n is equal to 0, all right, we have overlap here. 2 times 2 gives us 4. So that's the value of y equals 0. Now, we need to keep going. We need to now look when n is equal to 1. So that means we shift h of n minus k over to the right one more. This becomes h of 1 minus k. So now notice there's 2 overlaps here. So we have to take the product and sum the results. So I have 2 times 1, which is 2, plus 3 times 2, which is 6, and 6 and 2 give me 8. So this is the value at y equal 1. And now we have to slip and slide h of n minus k over one more. So now n is equal to 2. And notice there's overlap 3 times 1, which is 3. It's right here. 4 times 2 is 8. So 3 plus 8 is 11. So y of 2 is equal to 11. So notice what we're doing with our h of n minus k. We're just slipping and sliding it to the right, at, one at a time. And we have to just look at the product of how these two functions overlap and multiply them together and add the results. So there's one more. When n is equal to 3, we move h of n minus k over to the right one more, and now the only overlap is 4 times 1, which is 4. Notice everything else, there's only overlap with 0, so there's no product there. So y of 3 is 4, and now if we keep moving h of n minus k farther to the right, notice it doesn't overlap x of k anymore. So for we're going to get 0 for y equals for n equal 4, n equal 5, n equal 6. No, it doesn't matter how far we shift this thing, it's always going to end up being a 0. So finally, we can collect all our results, which are shown here, and we can plot them, and of course, we'll get the same result as we did before. We get the 4, 8, 11, and the 4, but as you can see, this took 10 steps here to get these results, whereas the simple method that we did in the activity was only maybe, probably less than half of this number of steps. I think it was maybe 4 steps total to get the same result. So my advice, would be for in the homework, for example, if you're having to do a discrete time convolution, use the simple method, and I think it'll be a little more efficient and save you some time. So that's it for part 1 of this video. We will get back together shortly for part 2 next. Goodbye.